Hi students, welcome back. In this week's video, we're going to do exponential functions. And the questions are from assignment 5.2. Right, before we go into the actual problem solving, let's look at an encouraging quote. And this is from Mr. Jim Ryan. And he said, motivation is what gets you started. Habit is what keeps you going. And this quote actually resonated with me very much because I started doing the video to help the students with their homework. And the students actually fed back to me that the videos helped them a lot, and that motivated me further and encouraged me to go on. As a result, it becomes a habit where I do it on a weekly basis. So likewise for you, do find a goal in your life, do find what motivates you, and then if you do it consistently, work hard towards it, it will become a habit. But I need to say that all these habits have to be good habits, right? Right, one of the habits that I've been doing it on my video is to do a recaps of the concepts before we actually go into the problem solving. So this question 1 is about sketching of the exponential functions. So let's look at the different types of the curves that we may encounter. Let's start off by having y equals to a to the power of x, and the values of a can take into different form. First of all, let's examine what happens when a is more than 1. So a is more than 1 meaning, example, I can have a curve that's y is equals to 2 to the power x or 3 to the power x, so on and so forth, right? So if that is the case, then this is how your curve will look like. When you substitute, when the x gets bigger and bigger, the values of y get bigger and bigger. Okay, you can actually use a calculator to help you with that, right? You can substitute different values of a and then see what happened to the values of y, the corresponding values, the values of y with the corresponding values of x. Okay, and you will see that when x increases, y also increases. Another way is to actually just go into these Desmos or any of those mathematical apps, graphing calculator, online graphing calculator, key in the values, key in y equals to a to the power x and observe what happened. Key in y equals 2 to the power x or 3 to the power x and observe the shape of the curve. Alright, and you'll see that there's one particular point that the curve will cut on the y-axis, and that is when you substitute x to be 0, you get y to be 1. Why is that so? That's, for example, I'm going to use this curve to demonstrate y equals to 2 to the power x. So when x is equals to 0, y is equals to 2 to the power of 0, and anything to the power of 0 is 1. Right, so therefore you will have this point on the y-intercept as 0, 1. Okay, right, another thing to take note is that there's a special name for this x-axis, okay, because your curve does not touch the x-axis at all. Right, you see this part of your curve, it will not touch the x-axis. Right, so therefore the x-axis is called the asymptote. Right, let's look at the second part of the curve, second kind of curve, and that is the values of what a. The values of a is between 0 and 1. So for example, it could be like half to the power x or 1/5 to the power of x. So this curve will look slightly different. Okay, it will be such that when your x increases, the values of y actually decreases. Okay, right, you can just, again, like what I've mentioned earlier, substitute in some values of x and to see the corresponding values of y. But on the y-intercept, it's still 0, 1. Okay, because when you substitute x to be 0, half to the power of 0 is 1, 1/5 to the power of 0 will be 1. Okay, that is another type. That is what happens when you are given y equals to 1 over a to the power x. So if that's the case, then it will depend on what you're looking at for the values of a, right? If your a is more than 1, okay, if your a is more than 1, okay, I'm going to label the curve here. This is 1a. This is, oh no, okay, I labeled it 1 and 2 already. Okay, so if the values of a is more than 1, that means that a is 2, right? So the curve you'll be getting will be 2. Curve 2, right? But if your a is between 0 and 1, meaning what you're getting is a fraction. So 1 divided by, let's say, half will give you 2. So the curve you'll be getting will be curve 1. Okay, so with these concepts in mind, let's go start to sketch the curve. Right, part A. Right, so if you look at the base that we have here, 4 is more than 1, so it satisfies number 1, curve number 1. Right. Which is such that when your x increases, your y increases also. So it goes this way. Okay, and let's look at part B. Right, y equals to, there should be a bracket here. Alright, let's examine the base. The base 1/3 is between 0 and 1. Between 0 and 1, so there will be curve 2. So that is when your x increases, your y decreases. Alright, let's look at part C. Part C, if okay, y is equals to pi to the power x. Now we all know that pi is estimated to be 3.14. So 3.14 is more than 1. So therefore you'll be getting the first type of a curve where your x increases, your y also increases. Okay, so basically this is how you actually remember the shapes of the exponential functions. Right, so if you remember what we have done in the earlier slide, the concepts, okay, for the first type of curve, alright, your a will be more than 1, right? And then for the second type of curve is this. Where your a is between 0 and 1. Right, so do you realize something? Do you realize the range that is given to you? Strictly more than 1 in the first type, in the first case, and then second case is strictly more than 0 and less than 1. Right, so why is it that so if you were to draw your number line, right, you will see that you need to be strictly more than 1 or strictly between 0 and 1. So in other words, you cannot take the values of a. So why is that so? Why is that so that a cannot take the value of 0? That's what we're going to do in question 2. So to manage this kind of questions, you just assume that what happened if a is 0. Right. So I can have different forms to represent a, right? We have learned all the rules of indices. If you were to recall, one of these is if you have a to the power negative n, you can write it as 1 over a to the power n, right? So I can actually also have something like this. Where I can rewrite it as a to the power negative 1 bracket x, and this will become 1 over a. Okay, right. So if we have a situation like that, and if we let a equals to 0, what happened? What you end up will be y is equals to 1 over 0, right? And 1 over 0, it's undefined. If you let a to be 0, then 1 over a will be 1 over 0, which is equals to undefined. Okay, so therefore, you can't actually have a curve. So therefore we can't have a curve, right? When a is equals to 0. Right, so how do you answer the questions? So to answer the questions, so these are the explanation, okay? These are the explanation, or rather the concepts. So how do you answer the question? So here comes the solution. So to answer the questions, we have to answer it as yes or no. Because the question says, can the base of the exponential function be 0? So the answer is no. No. The base a of the exponential function cannot be 0. So the next thing is justify your answer, right? So you just give an example. For example, if we have y equals to 1 over a to the power of x, and if a is equal to 0, 1 over 0 it's undefined, and hence the curve does not exist. Okay, so this is how you can answer question 2. Right, we'll see that exponential function is actually a very important concepts in many fields, such as, for example, in microbiology. Right, so this question is involving the concepts of microbiology is when you have this bacteria growing, right, and it can be actually modeled using these exponential functions. And we're asked to find the number of this E. coli bacteria at the beginning of the experiment. So the important concept here is what does it mean by beginning of the experiment? Beginning of experiment means the start of the experiment, And it always refers to the timing. Beginning or the start of the experiment will refer to the time. Wait, let me write it properly and not. Okay, it refers to the timing. So at the beginning of the experiment is when you substitute x equals to 0, because the variable x represent the time. X hours will remind you of we're talking about the time. So you substitute x equals to 0. So y will be 40. Okay, so 1.4 to the power of 0 will just give you 1, right? 1 times 40 is 40. So therefore, at the beginning of experiment, the number of Alright, so that's part A, relatively easy. So for part B, what happened is after 6 hours to see how much the bacteria has grown. So we're going to substitute t is equals to 6 into our exponential functions. Right. And okay, wait for a while. We're just going to use a calculator to evaluate the value. 40 301.181, so on and so forth. We're going to put it to 3 significant figure, that will be 301. So therefore the number of bacteria Alright, so that's how you answer question 3. Right, so if you look at the sequencing of the questions, we started off by sketching the exponential functions and then go into the direct applications of the exponential functions. So if you look at questions 8 now, it's slightly harder because it involves not just the curve, it's also in a straight line. So we need to find the how it looks like, a curve and a straight line. What happens? Okay, so not to worry, let's do it. So part I, let's look at the base of exponential function. 2.5 basically more than 1, so it is at exponential functions when x increases, y increases. So it will go this way up, and this value here is 1. Alright, so for your straight line, okay, to draw a straight line, basically how many points do you need? Imagine if you have only 1 point, then the straight line can be in any directions, right? Can be this direction, that direction, anything. You can actually make it a star, right? But this is not, if this is not what you want, because you want the straight line to be in a specific direction, then it needs to have 2 points, right? 2 points. If you want it to be in this direction, then your point must be there. If you want it to be in this direction, the point must be there, so on and so forth. Okay, so we need 2 points to draw a straight line. So we can have a little table, not the physical table. Alright, so I can let x to be 0. So 6 minus 0 will give you values for x, I can substitute x to be 0. So 6 minus 0 will give you y coordinate to be 6. So likewise, I can let y to be 0. So 6 minus x equals to 0, x will be 6. Okay, so I have 2 points there. Right, so 6 obviously is higher than 1, right? So 6 is here. And then maybe 6 here. Right, so please use a ruler to join these 2 points, because I basically cannot have anything else touching the screen than the tip of my stylus pen. So actually I'm doing quite a good job. Alright, so if you look at the diagram you have drawn, if you look at the diagram you have drawn, okay, there are actually two different shapes there, right? The curve, so we need to label it. We need to tell people that, hey, the name of this curve is y equals to 2.5x. Basically, you're just saying there are 2 persons there. We just need to identify them, identify by labeling them. Alright, so the name of this straight line will be y equals to 6 minus x. Okay, right, so that's part 1, pretty easy. So part 2 is state the number of solutions to the equations. Okay, so if you look at what you get at part 1, then you see that the number of solutions, it's actually this intersection point here, right? That point will be the solutions when you solved 2.5 to the power x equals to 6 minus x. But then we can't actually estimate the values. We can estimate the value, but just be estimated value, so it's not accurate. So therefore, from part 2, if you look at part 2, right, the questions did not say from the sketch, state the number of solutions. State the number. Oh, you just asked to state the number of solutions. So it's actually from the sketch. You're not asked to write down the solutions. Okay. So can you see the difference? If the question says that write down or solve. Okay, wait. If the question says solve the solution. Solve the equation or solution. Solve the solution. Okay, there's something wrong with me today. If the question says solve the equation, then basically your answer will be like something, right? Okay. Solution, that means x, something, yeah. That means your answer will be x equals to something. Well, you just need to really solve it. But here, we are not solving it. We're just asking for the number of solutions. So the number of solutions would mean the number of intersections point that you can find from part 1. So you can see that from part 1, there's only one intersection point. So therefore, there's only one solution. Okay. So from the sketch, that it's one solution to the equation. Okay, right. Alright, so okay, so we started with sketching of the curve, started with the direct applications, started with drawing a curve and a straight line, and seeing that there's only one solution from the example we've done. There could be 2 solutions or whatever, but the examples we have done earlier on is just one solution. And now let's look at question 10, where what you need to do is to find the exponential functions. That means you're not given the exponential functions, you're given the exponential curve, given 2 points. And then how do you go about finding the exponential functions? Right, so it's not difficult also. Okay, it's basically something that we've done before. right, where you are given a quadratic curve and you're given two sets of points, and you just solve them simultaneously, right? Because basically here what we are talking about is we need to find two unknowns, right? A and B. So these are the two unknowns we need to find, and we're given the values of x and y in terms of point forms. So there are two given points there, right? So all we need to do is just to substitute this point into the exponential functions as given. So this will be your, so you substitute your x coordinate to be 1, you substitute this guy to be x, this guy to be y. So you will have 6 is equals to a b to the power 1. So b to the power 1 is just b, right? So you can just don't have to write the 1 there. So that's equation 1. Then you substitute 0, 3. So your y coordinate will be 3. Your b will be 0. Huh? Oh, sorry. There's really something wrong with me today. Your y coordinate is 3. Your x coordinate is 0. Yeah. So that will give you 3 is equals to b to the power of 0 is 1. So 1 times a is 8. So a is equals to 3. Alright. Also, this is rather easy. So after finding the values of a, you just sub a equals to 3 into 1. And that you will get 3b is equals to 6 and b is equals to 6 divided by 3 equals to 2. Have you found anyone so happy solving doing homework? The person will be B, huh? You just heard me laughing and giggling. Okay, so that's how you solve this question. Very easy. Wow, this week's homework is rather manageable, huh? Yeah. Wow, so can you see how important exponential function can be? Right, exponential functions can be used in terms of microbiology, in terms of now we're talking about ectology. So I just Googled for the meaning of this word ectology, and it means it's a scientific study of animal behavior. Wow. So in this question here, we're studying the behavior of a fish populations. Okay, right. So it can be modeled using these exponential functions. Right. So find the number of fish in the lake just before the factory started operation. Or nearby a chemical factory. So you want to see the effects. Okay, how the bad effects, I suppose. It's not going to be good effects. The bad effects of what this chemical factory, what this chemical things that the factory, manufactured, produced, is going to affect our fish, populations of fish. Okay, so just before the factory started means the beginning, right? The beginning, it means the beginning. So the beginning refers to when t is equal to 0, right? So part 1, we sub t equals to 0. Right, so that will give me 600 2 plus e to the power of 0, because negative 0.2 times 0 will just give you 0. So e to the power of 0. So anything to the power of 0 is 1. So e to the power of 0 is 1, right? So that will be 2 plus 1, 3, right? 3 times 600 will be what? 1800. So when t is 0 at the beginning, okay, we have 1800 fishes, all right, in the lake. Right, so let's see what happened when time goes on. After 1 year, so your t, the units for t is in terms of months. So we need to convert 1 year to 12 months. So 1 year Right, so substitute t equals to 12 into p. So let's see how much we get. It will be 600 bracket 2 plus e to the power of negative 0.2 times 12. Alright, just hang on, let me use my calculator. I don't have a calculator, I'm using a calculator in the handphone. I hope it works. 600 times bracket 2 plus, okay, what's my exponential? Shift E. I have to key in negative 0.2 times 12, and then I need another bracket. Okay, I would get 1254.4.43 something something, estimated to 3 significant figure. Excuse me. So you look at the number 4, so round down to 1250 fishes. Oh my goodness, so we started off with 1800, now become 1250. So some fish died. That is very sad. Okay, so let's look at part 3. Part 3, what happened in the long run? That means 2 years, 3 years, 4 years, 5 years. What happened when t gets very large? Yes, if your t get very large, when t gets very large, then you realize that e to the power of negative 0.2t, right? When e gets very large, the value of e to the power of negative 0.2t will tend to be 0. Okay, you can try substituting very large value inside there, and you'll see that it gets very near to 0. Okay, almost 0. And if that's the case, then the populations of the fish would become stagnant at a value which will become 602 plus 0 and give you 1200. Okay, so now let's look at the last question. The last question is involving personal finance. So can you see how important the exponential functions are? It's used in microbiology, ecology. Now we're talking about finance. Alright, so we have exponential functions here. And there's several things that we need to take note what all this symbol represent. So PO represent your initial amount. So if you look at the questions, you're told that the initial amount that you put in the bank is $100. So let's put it down. And then R represent the rate. So the rate is given to be 5% per annum. So per annum means per year. And then of course T is how long, it's a period. How long you put your money in the bank. Alright, so first thing first, let's write down the formula. Okay, so we're going to find out what happened if I put the money inside the bank for 10 years. So we're going to substitute T to be 10. So initial amount is 100. Then e to the power of R is 5. So 5 times 10 over 100. So let's use a calculator to work this out. That is approximately 164.872. Right, so are we, oh, the question says give your answer correct to the nearest dollar. So to the nearest dollar, you look at the number 8 here, round it up, so 165. Right, so therefore the total amount of money after 10 years is $165. Okay, so you earn $65 by doing nothing. Just put your money in the bank and then you earn $65 for 10 years. Okay. That's not that's not that's quite okay lah, since you didn't do anything, just leave it there. Okay. Alright, let's look at part 2 of your last questions. So you're asked to use the graph given to estimate the number of years for your money to double. So your initial amount of money is $100. So for it to be double means you'll become $200. Right, so from the graph you can just draw a horizontal line, touch the curve, and then draw a vertical line. Okay, this is very bad. Let me try to draw a vertical line. Alright, and then it's estimated to be 14. Okay, it's not very clear, but yes, if you were to draw a better vertical line. Basically, I can't use a ruler. Basically, I can't just touch the screen except the tip of my stylus pen. Yeah, so it's about 14. Right, so therefore, the number of years for my money to double takes about 14 years. About lah. The number of years for my money to double, it's estimated to be 14. Okay, estimated to be 14. Right, so the last part of the questions, because if you look at the graph given, right, our graph does not actually go all the way up to $1,000. Right, so if you have $1,000, then do you think you will still take 14 years for your money to become 2,000? Right, so justify your answer. Okay, so what we're going to do is we are going to that means for whatever initial amount that you put in, we're going to disregard that. So imagine it can be like 2,000, 4,000, 5,000, 6,000, and then if you're going to double it, do you still think that you get about 14 years, estimated 14 years for your money to be doubled? So let's try to do it now. So what we are saying is your initial amount of money, we let it be PO. So initial amount right. We don't worry like whether it's 1,000, 2,000, 3,000. Then, but you want your final amount to be twice of it, right? So twice of PO means 2PO. Okay? Right, so we're going to substitute this value into our formula. So our formula is P equals to PO e to the power of 0.05t, right? So the P represent your final amount, which I can be substituted using 2PO. Then what do you see? So you realize that the PO and the PO can be cancelled off on both sides. In other words, and finally the equations you end up will be this. But you can go ahead to find the values of t, but we have not learned how to do logarithmic functions yet, so we're going to just stop here. But from here we can just clearly see that the initial amount does not really contribute to the time taken to double our money. Right, what we're saying is that even if you put 1,000, 2,000, 3,000 for it to be doubled, the number of time taken will still be around 14 years. Okay, so if you put 2,000, the amount of time taken will be roughly 14 years. If you want your money, if you put in 3,000 for it to become 6,000, the amount of time taken will also be roughly 14 years. Because from here we can see that the initial amount of money has no place in the final calculations for time. That means it does not contribute anything to it. Okay, it will take approximately 14 years for your money to be doubled using the exponential function given. Okay, so this is how you do the last part of your last question. Okay, so that's all folks. I see you again next week.